Welcome everybody. In this video we're going to talk about section 1.3. It's a quick section. It's about direction fields. Alright, so these are a useful way to get a handle on what the solution to a differential equation might look like. And the interesting thing here is that you can get this picture of what the solution might look like without even actually finding the solution. So let's go and see how this works. All right, so I'm going to start us off with a relatively simple differential equation. And by the way, actually, before I do this, I want to point out that the differential equations we're going to be looking at in this section are going to be differential equations of the form of this form. Y prime equals a function of x and y. Okay? Now, what we have here is we have the derivative on the left-hand side, right? Now remember what you learned about the derivative from calculus class. You learned that the derivative is the slope of the tangent line, okay? So let's just refresh our memory on what that means. If I had a graph of y of x, right? So at any point x here, I have the point x comma y, where the y coordinate is given by y of x. I have also the tangent line to the graph at this point. So I can imagine the tangent line going through here, just like that. And what is the slope of the tangent line? It is the derivative, right? So the slope of this line is just y prime of x, right? And we remember that the slope is just the change in y over the change in x between any 2 points on that line. Okay? So we're going to use this knowledge to get an idea of what the graph to a differential equation may look like. Okay? So let us start with the differential equation. The one I'm going to start with is this one. Y prime equals negative x over y. We're going to just start drawing a graph. Okay? So I'm going to draw some axes here. I have an x-axis and a y-axis. Okay? And then I'm going to look at various points. Okay, and I'm going to try to get a picture of what the solution might be doing at these different points. Okay, so I'm going to go here, 1, 2, 3 on the x-axis, and then 1, 2, 3 up on the y, -1, -2, -3 down on the x, on the y, and then -1, -2, -3 on the y. And then we get all these points that we are going to check. Right, we have this grid that we are going to look at. Okay? And what I want to do is just draw a little picture of the tangent line at each point. Okay? So let's go over to this point here, 1, 1. Okay? Now at 1, 1, x is 1 and y is 1. So we can just plug those in. All right? When x is 1 and y is 1, this quantity is -1. So therefore, y prime is -1. So if the solution happens to go through this point, we know that it's going to have slope -1. So what I'm going to do is draw a little line with slope -1 there, just like that. Now let's go over to this point over here, 2, 1. Okay, x is 2, y is 1, so y prime is equal to -2. That means the slope, if the solution goes through this point, its slope will have to be -2. So I'm drawing a little line with slope -2. And then over here, 3, 1, 3 over 1 is 3, -3, so the slope is -3. What about over here, 0, 1? Well, here we have 0 divided by 1, so I get 0. The slope is 0. And what about over here, -1, 1? Well, now I get 1 over here, so the slope is 1. My pen is giving me a hard time. It's not staying staying out. Okay, then over here, negative 2, 1, plug those numbers in, we get the slope is 2. Negative 3, 1, we get the slope is positive 3. And you keep doing this. You go to every point, plug the values in, and get the value of y prime. And we get the slope at that point. So here we just keep getting 0, right? Because whenever x is 0, this thing's going to be 0. When x and y are equal, we get negative 1. So these are all going to have slope negative 1. When x and y are negatives, we get slope positive 1. Right? So I'll just keep filling this in. Right? You get something like this. And we can go down to the negative part of the y-axis as well, these quadrants down here. And we get this. This is called a slope or a direction field. Okay? I think the book calls it a direction field. And this is really useful because what it's telling us is if the solution goes through these points, the graph has to have these line segments that we drew in blue as the tangent lines. So this is giving us a picture of what the solution ought to look like. Okay, so for instance, suppose I gave you this differential equation, but I told you that also I'm going to give you an initial condition. I'm going to say y of 0 is equal to 2. So this, and if you look back in a previous video, we dealt with verifying solutions to differential equations with a condition. Okay, so I'm just doing that same thing. Here's the differential equation, here's the condition. I'm not telling you the solution, but we can draw a graph of what it looks like. Because if y of 0 equals 2, that means when x is 0, y is 2. We are going through this point right here. And if I just draw a curve so that its tangent lines line up with these lines, I can see that that curve would have to do something like this. It's going to have to go around like that. That slope field, or that direction field, is demanding that this be a circle with radius 2. Okay? And if I said something like y of 0 equals 1, well, that would be this solution over here. If I said y of 2 equals 1, well, now I'm saying that when x is 2, y is 1, that's this solution over here. So we just get a bunch of concentric, terribly drawn circles. They should be actually much more circular than this. I'm just doing a bad job of drawing them, right? So given the different initial conditions here, we get different curves. And we can just see that from the direction field. Now they look like circles, right? So this suggests that the solution may actually be the function that defines a circle. And so you could actually check that. And it's a good exercise. I invite you to do this. You know how to write down the function that describes a circle, right? So write it down as a function and verify that it does indeed satisfy this differential equation. That's a good exercise for you to do. Okay? So these are actually supposed to be exactly circles. Okay, so let's do this again. Let's take a look at a different differential equation, just slightly different, and let's see what happens. I'm going to look at y prime equals x over y. So I'm just going to take the negative sign off. That's all I'm doing, taking the negative sign off. What do you think that's going to do to this direction field? How is it going to change? Is it going to make the curves a lot different or just a little different? Maybe the same? So think about that. Now let's go ahead and set up our grid. And now we're going to draw our direction field. All right? Now, please, I invite you to stop the video and try to sketch it on your own. And then, pause this video, do it on your own, and then unpause it, and then we'll check our answers together, okay? So let's go ahead and, assuming you've done that, we're going to go through this. Okay, so at the point 1, 1, for instance, 1 divided by 1 is 1, so I get slope 1, right? Also, when I'm at 2, 2, I'm going to get 1. And when I'm at 3, 3, I'm going to get 1. And also when I'm down here, I'm going to get 1. Just plug those coordinates in, and you get 1. What if I go to negative 1, 1? Well, then I'm getting negative 1. So lines of slope negative 1. Now, what if I'm 2, 1? Well, then I get 2. And if I'm 3, 1, I get 3. And if we keep sketching these out, okay, so we have a slope field that looks like this. Okay, now let me specify some conditions. Suppose I was looking at this differential equation and I wanted the solution that satisfied y of 0 equals 2 again. Okay, well, if y of 0 equals 2, I'm starting here. Now let's draw the curve that uses these line segments as its tangent lines. Well, it looks like it's going to go something like this. And what about that other initial condition? Well, let's go ahead and do the same ones. Y of 0 equals 1. What if I do y of 2 equals 1? Looks like we're getting curves like this. What do these curves look like to you? They are hyperbolas, right? So, in fact, they are exactly hyperbolas. And you know the standard how to write down a function that defines a hyperbola. If you don't, please look it up in an algebra or a calculus text and write that down and verify that a standard hyperbola does really satisfy this differential equation. These are all hyperbolas. Not only hyperbolas are we getting, though. Do you see some other curves we're getting? What if I started with the initial condition y of 1 equals 1? Well, now I'm starting here. Now I'm just following this straight line, right? So we also have, and if I said y of negative 1 equals 1, I'd have this line here, right? So we also get some lines in here. Now these lines can be thought of as, actually, I shouldn't draw these lines all the way through. What's really happening, I think maybe you should think about it as the line coming down and stopping, and then we're picking up as where we left off and going to a different line. So it's kind of like a hyperbola that got scrunched down to a point. So instead of being rounded at the bottom, it's now just pointy at the bottom. Okay? So you can kind of think of this V shape as just an extreme hyperbola. All right, so this is a way, without actually finding the solution, we are able to get an idea of what it looks like. And that can be incredibly important because a lot of times when you deal with differential equations, the exact solution isn't always all the things that you need. You may not even need that. What you need to understand is the behavior of the solution. What happens when I let time go to infinity? What happens after a long period of time? Is the population of rabbits going to diminish to 0? Are they going to go extinct? Or are they going to regulate and kind of level off and become a stable population? So just understanding the long-term behavior of the solution is all we might need to be after. And so that's something that you can grasp just from these pictures. So you don't actually have to solve the differential equation. You just have to be able to, by looking at these direction fields, you can get an idea of what happens. So that's incredibly important. I just want to point out in the book, when you read through that chapter, there are some examples of other slope fields. So let's just take a look at some of these. You have the book for yourself, so I'll let you take your time on these. But you can see kind of the crazy slope fields that you can get. Can look at, here's the Differential equation. It looks like they forgot the prime on the y here. There should be a prime on the y. Here's this differential equation and the corresponding slope fields. And you can see how the functions behave quite a bit differently depending on where you start. Some of them kind of go up this way, and some of them go down. So they have quite a bit different behavior. And we have a slope field here. You know, it's kind of like flowing through a fluid. You know, you drop a ping pong ball in a river and just watch where it goes. That's kind of what these, that's essentially, that's one way to think about what these curves are doing. They're giving you the directions, the paths that a particle would flow if you dropped it into the current. Here's another one, a slope field for this differential equation. And they have some other one. Here's one that we looked at, y prime equals negative x over y, right? And this is exactly what we saw. This is drawn with a lot more, you know, slopes than I drew, but you can see what's going on here. And we have some really interesting one here. Some really crazy twisting going on, right? And you can see what one of the solutions looks like. A really crazy curve. I mean, just try to imagine trying to write down the function that defines that curve. It'd be very difficult, but we can see what it looks like, and it comes from a not too crazy differential equation. Okay, so that's it for section 1.3, slope fields. I will see you in the next video.